So welcome everybody. In today's lecture, we will talk about coherent phase shift keying. So in the previous lecture, we talked about modulation in general, amplitude shift keying, frequency shift keying, phase shift keying, and we introduced you to some of the new modulation schemes that are appearing in the literature, and we said that it's not really difficult to come up with novel modulation schemes if you can utilize new features to encode your data on. So in today's lecture, we will be focusing on studying phase shift keying and particularly binary phase shift keying. Phase shift keying can be binary, two level or two cases phase shift keying, 4 cases phase shift keying, or M-array phase shift keying. Means it has many levels in terms of phase, not in terms of amplitude. And what's then the meaning of the word coherent? Remember with me, we said coherent means that the transmitter and receiver have to agree on the phase of the carrier that they use to transmit and send their information by its help. So this means that perfect synchronization should be maintained between the transmitter and receiver. Any mismatch will prevent you from decoding your data properly. And this is really a drawback that we need to avoid as much as we can. What's the opposite of coherent? Non-coherent. And when you hear the word non-coherent, what do you remember? That it's simple, the receiver structure is not that complicated because you don't need to maintain the phase information of the subcarrier of the carrier. But at the other side, your performance is not that good. It's actually because it's simple detection. Simplicity always comes with some drawbacks. One of the drawbacks of the simple detection that non-coherent schemes deliver is not being able to deliver very good bit error rate. While coherent makes sure that your bit error rate is very good, but at the expense of some complexity. So having said this, we are going to study coherent phase shift keying. Coherent and particularly binary phase shift keying. So in this system, what do? We have pair of signals. Since we said binary, then how many different signals I can have? How many different signals? 2. Is that right? Because binary, this is binary system. What are the signals that I can transmit? Either S1 of t or S2 of t. So S1 of t, since you are using passband communication and transmission, you need to use a carrier. What's the carrier that I use? Cosine, the sinusoidal, and I use this carrier to encode the information bits 0 or 1 that I want to transmit. So for example, when I send 1, I make the phase of the carrier 0. So this plus 0, there is no phase. But when I have 0 and I want to send 0, I make the phase of the carrier frequency equal to pi plus pi. Now I know when cosine something plus added to pi, this gives you the negative amplitude of the carrier itself. So what does this tell you? If you have 1, you send this signal, which is this value, which is constant amplitude, multiplied by the cosine. Yes, cosine is the carrier and this is the amplitude. When you have 0, you basically send the negative of the amplitude multiplied by cosine. So one might say that this looks like polar non-return to 0 signaling, because in that case we were assigning plus a to 1 and minus a to 0. And this seems to be similar. I tell you, yes, this is a special case where binary phase shift keying, although you are changing the phase, but this turns out to be changing the amplitude value from positive to negative, negative to positive, with the carrier, That there was no carrier in BCM, pulse code modulation, binary, polar non-return to zero. You remember that? When we have BCM and we said represent the data bits using polar non-return to zero. Suppose you have this sequence 0, 0, 1, 0. How do you represent that in polar non-return to zero? Question in the exam, I brought it. 0 minus A, 1 plus A, and 0 minus A. So this was the signal. What I want you to know is that this is minus A, this is plus A, and this is minus A, and this was the reference, the 0 level. So similarly here you have, if you have 0, you have this amplitude. If you have 1, you have positive amplitude. If you have 0, you have negative amplitude. So it has some symmetry, as you can see. Yes? But this is a special case. You cannot generalize. Just for the case when you have binary phase shift keying, it seems similar to polar non-return to zero because of that feature, that when you change the phase by pi, it becomes the negative of the amplitude of the sinusoidal. So this applies your signal that you are transmitting. T is bounded between 0 and the duration of the bit, which is denoted by TB, and EB is the transmitted signal energy per bit. So can I ask someone to find the energy of a sinusoidal signal? If I tell you this, I give you a signal in the exam, and this signal is A sine 2 by FC T. FC is the carrier and T is the time and sine is the sinusoidal and A is the amplitude. I tell you, find the energy of this signal. What's the energy? Electrical circuit theory 1. Energy is equal to power multiplied by time. Is that true? Power multiplied by time. What's the power of this signal? A square over 2, because this is sinusoidal. This is the power. You put it here. And what's the duration? TB, because this over a TB period. So this is the energy of your signal. So this is EB. Here, it's EB. If you substitute the value of EB that I just found here, in here, do you know what will you get? A alone, amplitude. Is everybody with us? Is everybody focusing with me? You will get A. This means that you can write this instead of square root of 2EB over TB, you can put A multiplied by cosine 2 pi FCT. There is a condition also when you use the carrier frequency. The value of the carrier frequency should be selected in such a way that it's much greater than the bit rate. What does this mean? That the FC has to fulfill this condition. It's greater than N times 1 over TB. What does this tell you physically when you think about it? What does this mean? This means the variation in the carrier faster than the variation in your data stream. Yes? How often your data stream changes? Less than how often your carrier changes. If this condition is not satisfied, your modulation will not work properly. So remember, keep this in mind. The variation in your carrier must be greater than the variation of your bit rate. Data stream changes. Okay? This is important so that the carrier can carry and represent the information, because otherwise, if the variation, give me an example where the variation of the data bit is greater than the variation of the carrier frequency. The variation in that case, you have the carrier like this. Yes, this is the carrier. And you have the variation something like this. So how the carrier is going to change its phase according to the data variation, it's impossible. Even if it changes how, it should be, the carrier should be greater. You got it? Some people got it. I'm happy for that. That's very good. So now, as I said before, in order to send your information, you need a carrier. And what do we call that carrier? We call it a basis. You remember from linear algebra 101? You took it in your second year after calculus 1, calculus 2. You were asked to determine the eigenvalues and eigenvectors. These eigenvectors of the matrix are bases, are basically can be used as carriers. Did you study singular value decomposition? Gram-Schmidt. Gram-Schmidt is a way, a method to find orthogonal bases. Now, orthogonal bases, we like them in communication. Anybody can tell me why we like too much orthogonal bases? Why we like too much orthogonal bases? Like we like sine with cosine. Why? We like to have too many orthogonal bases. Why? Why? Anybody can say why? Because when you have orthogonal, what orthogonal means? Their dot product 0 means their contribution to each other 0. In communication science, this means no interference between them. And if there is no interference between them, you have maximum signal to noise ratio and you have better error rate. Yes, got it? See the math, how it helps you in understanding communication, and it makes sense when you connect your courses with each other. That's why we love studying math, because it helps. It helps, and I told you, if you can come up, we have sine and cosine orthogonal to each other. If you can come up with a third signal, this is homework for you to think about it. Try to come up with another signal that's orthogonal to both sine and cosine. If you can come up with this signal, you will get 100 in your final. You don't need to offer the final. Come up with a signal. I don't know what's this signal. In such a way, it's orthogonal to both sine and cosine simultaneously. What does this mean? If you take the dot product between this signal and sine, it should be, the result should be 0. And this signal with cosine, the result should be 0 too. Two conditions. The signal, any signal, x. You have two conditions to fulfill. Integration of x of t multiplied by sine of t is 0. This is the first condition. The second condition, integration of x of t multiplied by cosine equal also 0. What's this signal? This is the question. What's x? If you can find a signal that fulfills this condition, I'll give you 100. No need to offer the final. This is very good opportunity for you to think, challenge yourself. Okay, everybody happy? Everybody understanding what I'm saying about this carrier and the variation and why they are important and how math help in understanding the basic concept of communication? So, since we have 2 bits we are transmitting, we have 2 signals, how many basis function we need? Basically, we need only 1. But we have 2 pair of symbols. We have S1 of t, which represents bit 1, and this represents bit 0. we can see that only one basis function, which means carrier. See, between two parentheses, I'm putting the meaning of basis function, carrier, is needed to represent both S1 of t and S2 of t. How do you represent them? Let's see. You have this basis function, which is the carrier, and this is the value of the carrier. You have only cosine, and this is the amplitude of the basis function, square root of 2 over tb. And it's defined over the duration. T is bounded between 0 and tb. Now we can rewrite S1 of t, your first signal that represents 1, as the quantity equal to square root of EB, where EB is the energy, multiplied by the basis function phi 1 of t. And this 2 of t is equal to the negative of that. It's just like this, but with negative. Why? From where the negative is coming? From the plus pi. Plus pi, cosine something plus pi makes it negative, the amplitude of the carrier, from math also. So, now plot the region. Region 1 for signal S1 of t, which carries plus 1. And region 2 for S2 of t, which represents 0. So, you have message point 1, message point 2, and you have a boundary between them. This is the area where you receive your 1s, this is the area you receive your 0s, and this is the boundary between them, and you need to decide. Based on where you receive your signal, you decide. If you receive the received signal is coming from the air to the antenna, and the signal came here exactly. Where do you think that this signal, what do you think this signal is? Carrying 0 or 1? Carrying 1, because it's in the region of 1. If it falls here, then you decode it as 0 because it's in this region. Then what do we need to do here? We need to calculate the error probability. This is the way you draw the constellation diagram. How do you draw the constellation diagram? If I ask you, you just take the signal S1 of t, take the two signals S1 of t, S2 of t, find their projection. This is mathematical expression, mathematical word. Find the projection of a vector on a basis function. You know it from calculus 3. You took calculus 3. The projection of something on a basis function. How do you find it? Well, from physics even. When I give you this, for example, this vector, yes, and tell you this is theta, find the projection of this vector in the direction of x. What do? Dot multiplication between this vector and this vector. You just take the value, this vector S1, let's say, S1 of t, you take the integration of S1 along the basis function here, which let's say theta 1 of t is this value. It's basically the projection. It's basically your signal point. And then the projection at the y-axis. At the y-axis, you multiply it by another phi 2 of t, or phi 1 with different phase. In order to draw the constellation diagram, we need to find the projection of each transmitted symbol, S1 of t, S2 of t, on the basis function, which is phi 1 of t. So to find the symbol in region 1, you just integrate. This integration, anybody tells me what's this integration? This is dot product operation. Yes, what's dot product operation? Integration of the first signal multiplied by the second signal, find the result. If the result is 0, what does this mean? The two signals are orthogonal to each other. If they are not, if it's not 0, then this means that they are correlated to each other. There is something common in between them. And this, after you find this integration, the result is plus square root of EB. The projection of the second symbol S2 of t on the basis function phi 1 of t is given as the projection of the second signal. This is 2. Look, how do we read it? 2 over basis function 1, which is equal to square root of S2 of t phi 1 of t delta t over the interval from 0 to tb, which is equal to, after you find the integration, you will find the answer to be minus square root of EB. Is that clear? Is that easy? Not difficult. And then after you find these values, you just come and draw them here. Here you put 1 point and here another point. This is square root of EB, this is minus square root of EB. And you have one basis function, which is this phi. And you put decision boundary. The decision boundary, since the amplitude of 0 is same as the amplitude of 1, 1 for plus, 1 for minus, then what's the optimal threshold? The one exactly in between them. What's the one exactly in between them? It's mean. What's the mean of plus square root of EB and minus square root of EB? 0. That's the mean here. This point is equally distant from both points, S1 and S2. Clear? That's very intuitive actually. Now, here is the question. Here is the thing that we were asked before in the exam, and we are going to ask it one more time, and this is how we solve it. Now, having explained binary PSK, now can you calculate the error probability of this scheme, of this modulation, over an additive wide Gaussian noise channel? It should be possible. How do you find the probability, the average probability? You start with this. Everybody must start with this. You tell me the average, I have error. This is the average probability of error. I have two cases for error. When I send 0 and receive 1, when I send 1 and receive 0. This is the simplest case for the case of binary, when you have only two levels. What's the probability of error in this case? Probability of sending 0 multiplied by the error probability you send 0 and receive 1 plus probability of sending 1 multiplied by the probability of sending 1 and receiving 0. What's the probability of sending 0? This or this. What's this probability? Can you tell me? Half. Why? Because I can send only 0 or 1. What's the probability that we send 0 if it's random? 50. Here half, here half. Now what's left to find this value and this value? What's the probability here? B10. This is conditional probability. You send 0 and receive 1. This is the error. Where can you see this? Here. You send 0, here's the 0, and unfortunately you receive it here. This is affected by what? By noise. What's the distribution of noise? Normal Gaussian distribution. So you need to, your error function is function of the Gaussian distribution. You just need to determine the mean of this function and the variance. What's the mean? What's the variance? This is see, this is B10. This formula. What's this formula? Anybody can tell me? This is the Gaussian function I gave you after 1 over square root of 2 pi sigma square. Here it's automatically substituted, but let's substitute them. 2 pi sigma square. What's sigma square? In naught over 2. Yes? Here this 1 over basically in the function that I gave you. 2 pi sigma square. What's sigma square? In naught over 2. So 2 with 2 goes, what's left? Pi in naught. And here, what's the exponential of minus? This is e to minus x1 minus the signal you are transmitting over 2 sigma square. Is that true? What's sigma square? In naught over 2. In naught over 2. 2 with 2 goes. Remains what? Only in naught. You take it out here. And x, I know my x is general function, the signal. And what's the value of S21? The mean of S21? Minus square root of EB. That's why this becomes plus. When you find this, it's enough. I consider that you found what's B10. You just come and substitute it here. Yes, here in this formula, B10. And also, you do the same for the other case where you send 1 and receive 0 in error. So basically, after you calculate all these together, you are able to find the error probability. See, this is the receiver that I consider. Detector here. What's the detector here? Is comparator. If it is greater than or less than. If it is greater than 0, it's 1. If it is less than 0, the bit was 0 then. And this is the signal you transmit. You receive. Xi of t is equal to the signal you transmitted, Si multiplied, added to noise, n. So this is basically what I want you to do. Exactly. This is for the case where you send 0 and receive 1 in error. When you send 0, what's the signal value? Minus square root of EB. Yes? And since there is minus already here, minus becomes plus. So now to simplify your derivation, I don't need you now to simplify anything. You can just stop there and I will consider it correct. But you can simplify it more. You say this exponential, this whole value, this value, you can consider it z square. Z square, this. Yes? And you just, after you substitute everything, you can represent this function in terms of the ERFC, error complementary error function. Error complementary error function is basically the integration of Gaussian normal distribution from a threshold to infinity. Yes? And this basically equal to this. So anyone you find, it's fine and it's okay. So what's the final total error probability? Let's come. I found it here, B10 half. Yes, half ERFC. Yes? Yes or no? Come and substitute it here in the equation. Half multiplied by half ERFC. And here also half multiplied by half ERFC. Half multiplied by half, 1 over 4. Plus 1 over 4, 2 over 4. 2 over 4 is equal to 1 over 2. So the total error probability, 1 over 2 ERFC. Clear? This is what I wanted you exactly to do. And again, if I bring something similar, you need to proceed in this manner. Good. I will be very upset, very angry, very disappointed, very frustrated if I bring a similar question and you make again the same mistake. I will put on everything wrong, because this means that you were not focused with me, you are ignoring the lecture, and you are, if I bring anything similar in the exam and you don't get it full mark, I will be really very angry with you. Because there is no way we can explain this in a much simpler way. 2 times I explained it. brought it in the exam. Don't get scared of the shape of the question. The longer the question, the more details it gives you. So don't be afraid. Don't be scared. Ask and read calmly and you will find the solution. But also remember these lectures. Remember what I mentioned and say here. It will help you. This is fundamental. Now in the future when you go and work with any group or any company and tell you the company provide me performance analysis or estimate, tell me what would be the performance of my scheme when this happens. You need to do these things. Or if you go and do PhD or research or this. This is the fundamental. Later on you can change the distribution function to Rayleigh, Raytian, Nagagami. But if you do it for Gaussian, then there is possibility you can do it for others. As long as you understand the basic concept very well, profoundly. Clear? It's very similar to the previous case and the previous question. So this is the average probability of error we derived. So if someone asks you what's the average probability of error for binary BPSK, it's basically this value. And to find it, this basically, we can take it from lookup table because I told you we cannot find the integration of exponential to e to minus x squared. That's why we find it numerically and we put the values in a table so that anybody can find the error probability function, the error probability value at any EB over a node. So this is how we find the error probability. Now, how do we generate BPSK? How do we generate BPSK? Simple. You take the bits, yes, then 0, you map it to minus square root of EB, and 1 to plus square root of EB, which is this, what we call this, polar non-return to 0. You have sequence 0, 1, 0, 1, 0, 1. Yes? You map 1 to plus and 0 to minus, and then what do? You multiply by the carrier cosine directly. You get binary phase shift keying. So what do? You take the binary data sequence, you multiply it by polar non-return to 0 level encoder, which gives you this shape. Yes? And then you multiply it by the basis function, which is the carrier. Is that clear? And then you take the binary phase shift keying signal S of t. How do you detect? Now this is how we modulate, this is how we transmit. How do you detect? You take the signal and you multiply by the carrier that you used at the transmitter. That's why we call it coherent. We know the carrier exactly. We can generate the same carrier at the receiver, multiply it by the signal, and then integrate over a period of the bit. Over a period of 1 bit, you integrate your function. And then you compare with a threshold. What's the optimal threshold here? 0. Your optimal threshold depends on what? Depends on the way you map the 0 and 1 in polar non-return to 0. Now I can play with this in the final. I can tell you map 0, I want you to map 0 to minus a, but 1, I want 1 to be mapped to 2a. What's the optimal threshold? Anybody puts 0, then this is wrong. What's the optimal threshold? The optimal threshold is plus. You have 3 A's. 3. What's half distance? 3 over 2. 3 over 2. You go from minus a, 3 over 2. So it becomes a over 2, the optimal threshold. Yes? Is everybody with me? A over 2. It's the optimal distance between the 2 points to detect correctly. It's not anymore 0. You need to update this and make the threshold a over 2. If you, for example, if your signal doesn't support minus, doesn't support negative value of your The channel doesn't support negative value of your signal. What do? You need to shift. You are not allowed. So what's your optimal threshold? 0? Not anymore. You need to update it according to the values, the new values you have. But for this special case, if the signal is greater than 0, you choose 1. If it is less than 0, you choose 0. Then what's left? You know what's binary BPSK? You know how to find its error probability. You know how to generate it, how to detect it, how to plot the constellation diagram. You also need to know how to draw the power spectral density, the shape of the signal in the frequency domain. The power spectral density of the binary phase shift keying signal can be found just like the way you found it for polar non-return to zero signaling, because it has the same structure. And this assumption is valid for BPSK because BPSK is generated by using polar non-return to zero signaling in the baseband. And after you do the math and calculate the Fourier transform of your signal, you will find that the power spectral density can be plotted according to this red curve. So this is the power spectral density and this is its equation. With this, we finish our discussion about binary phase shift keying, and I hope you understand it now, its concepts, how to generate it, how to detect it, how to find its power spectral density, and most importantly, how to derive and find the bit error rate or average probability, and also be aware of the optimal threshold. The optimal threshold is not always 1, it's not always 0, it depends on the values of the amplitude of your signal. So thank you very much and meet you next lecture.